Hi everyone, I'm Graham Maidment and I'm Professor of Refrigeration here at London South Bank University, and I'm delighted to be chairing today's event on the incredible impact of an amazing man, Lord Kelvin. And Lord Kelvin was really influential in cooling. Cooling is very critical to our lives today, and from anywhere from keeping our food safe, maintaining an internal environment, producing and storing chemicals and pharmaceuticals, and also running the data centres that are streaming this event today. 2024 marks the 200th anniversary of the birth of Lord Kelvin. He was one of the pioneers of refrigeration. William Thompson was his name, and he was the first Baron Kelvin. He's one of the most eminent physicists of the 19th century and considered to be one of the founding fathers of refrigeration. He was also an amazing engineer, and I'm delighted to be able to introduce the event today. And over the next half an hour, 3/4 of an hour, we're going to celebrate his life. We're going to talk about some of the incredible impact that he had on us today, and we're going to link it to some of the challenges that are in the future. And I'm joined here by two amazing people, Helen Czerski and also Alex Jar. Helen, Dr. Helen Czerski, is from the University College of London. She's a physicist, first and foremost, but I think she's got a few other hats she wears as well, which she'll tell us about. And Alex Jar is Science and Technology Editor for The Economist, and again, he can introduce himself in a minute. To start, I'm going to just throw into the mix a bit of a question about cooling in general, and I'll be interested to know how cooling impacts on your lives. And maybe you can start with introducing yourself and then perhaps follow in with a response to that question.
Yeah, well, I'm a physicist who these days uses that physics to study the ocean, and I write about scientific ideas and share them, so that's me. But the biggest impression, I think most of the places cooling touch our lives we don't actually see. And my biggest impression of this was formed a few years ago for a TV documentary when I went to one of the, I can't remember, it might have been Ocado. It was their food distribution warehouse, and they had a -22 room, which is where they kept all the frozen things. And they had this amazing factory full of robots, there were robots that were kind of running around and distributing everything. And they were very proud of their robots. And we didn't care about the robots. We just wanted to get to this freezer and film something in the freezer about temperature. But it was an astonishing place because it was this huge room. It was at -22. Everyone in there was kind of in Arctic gear. And they were rushing around. They weren't interested in it. We were standing in the middle of it trying to film. They were pushing past because they were cold. But all around us, there were banks of frozen carrots and potatoes and all these things that we just see in freezers in the supermarket. And what was going on was that this is the middle of a chain of cold that we don't appreciate, that sits behind our modern food systems. And, you might buy frozen carrots, or they're picked, they're frozen, and then they never warm up, right? They're carried on a frozen lorry, put in a frozen warehouse, transport, every stage of the process is cold. And then we barely think about that. And even in our freezer, in our own kitchen, it's cold. And yet when we take them out, we never really think about the cold that made it possible. And so when I think about, cold, refrigeration touch our lives in many ways, but I think that's one of the most impressive things, the fact that you can keep things, it's hard to keep things cold, and you can keep an entire distribution chain cold. For all those miles and all those months and days, that's an incredible thing, and we completely take it for granted.
It's very, very hidden, unfortunately, and it does an amazing job, and it's great that you're able to bring that to life. Alok, what about you? How does cooling impact on your life? Perhaps at home, or perhaps with your family? Perhaps you can tell us a little bit about. Also, introduce yourself as well, please.
So I'm Alex Jar. I'm a science and technology journalist. And so I've spent most of my career writing about technologies and the way that they impact our lives, and kind of all the way from the things we use every day to the latest developments in cosmology or any of those sorts of things. I think one of the things that people talk about when it comes to journalism around science is that you've got to get people interested, so you write about space or dinosaurs, one of the two things. And definitely in both cases, cold is important. But for me, I think the way that I think about cooling and cold is that I don't really like the cold very much at all. I get cold in a hot room, and so that's my sort of personal feeling there. I don't know if it's genetic or something else, but I get cold very easily. But I think about it more and more and more at a professional level, because one of the things I cover is climate change a lot, and we'll talk about that, I'm sure. And we talk about how the world is warming up, and what keeps occurring to me is that you think about history, about how civilizations fell on the earth, and certain parts of the world, before we knew about climate change, became inhabitable only because you were able to cool that place. So let's think about the southern states of the United States, for example, which was swampy and steamy and all of those things. And the only reason that those states became livable was because of the invention of air conditioning. And so it's one of these technology stories which, we don't think about now because it's just everywhere, air conditioning. And it's, in a way, magical. And that's the great thing about technology that works. It's just magical. It's there in the background, as Helen said, with minus 22 degrees fridges. When you think about it, it's kind of crazy, but you don't think about it. And that's what the amazing thing about a lot of science and technology is that it abstracts itself away. And hopefully we'll talk about some of that technology today. But the idea that, those parts of the world in history were made livable because of air conditioning. The economy of the world increased as a result. More parts of the world are livable. We're going to have to do all of that all over again, but in a completely new way. And I think about that as a journalist a lot, because I think, well, we're already struggling to reduce emissions in all sorts of different ways and find sustainable ways of using chemicals to cool things down or fly planes or whatever else. This is another challenge I don't think we think about enough, which is that how do you build new innovative systems to do that air conditioning, to make people's lives comfortable? Because ultimately, I do care about people, and I think that they deserve to live in decent conditions. And so therefore, how do you make their lives more comfortable when you know that large parts of the world are going to be unlivable? And it has all sorts of impacts. So I think about that a lot. And in terms of how it impacts my daily life, any new innovations in technology I like to write about or send my reporters out to look at. If there are parts of the world's governments that are thinking about this more, I like to think about it. So those are the things that I actively think about and I actively want to know more about.
Really, you've raised a really important point about what the world would be like without cooling, and the analogy of the area of the swamps and not being able to live is really interesting. I'll turn back to Helen, if that's okay. Can you imagine what else the impact of would be without refrigeration, air conditioning, cooling today? What other impacts? What would we be like? Perhaps you could describe your thoughts on this.
Well, it does refrigeration. For medicine, for example, there are many medicines that need to be kept cool. We've got used to a standard of life. We've got used to a global economy. And you have to, one of the rules of biology is that if you warm it up, things speed up. And so if you cool it down, you slow down decay. And the number, we completely take it for granted that we can control that process. And really it's about the ability to control it rather than the fact that it's hot or cold. We have if you look at the huge range of temperature that you could have, we live in a very specific, narrow range of it. And keeping things there, as Alex said, it's important for our comfort because we're kind of, weedy creatures. We're not like cats and dogs that can run around without clothes. We need clothes and technology to keep ourselves in that narrow bound. And we also use it to control our environment. So really, you could almost point at any part of the modern world and say that wouldn't be possible without cooling. Even, fossil fuels, which we now read, liquefied natural gas and things, there's a cold chain there as well. So basically, if you go back far enough, you'll find that refrigeration is a critical part of almost any aspect of our modern world, because it's what gives us control over our world, controls the rate of decay, controls the speed of chemical reactions, and it is a really important lever we can pull to exert that control and to make the world convenient for us, which we're very keen on as humans.
Yeah, fantastic. Early in your comments, you use the minus 22. And by minus 22, I think you meant minus 22 degrees C.
Yes.
The alternative way which we might measure temperature is Kelvin. And that brings us on to the reason why we're here today is to talk about this amazing person, Lord Kelvin. And I don't know whether, Helen, I'm going to ask you initially, perhaps, can we start to talk about, can we start to form some sort of a picture about Lord Kelvin actually from the start of his life, and actually how, I wanted to try to build a picture for everyone so you can see how he started from a very young person to actually how he came up with this fantastic temperature scale and how it impacted on people's lives, etc. Perhaps you can start by telling us a little bit about his early life.
Well, of course, for most of his life, he wasn't Lord Kelvin, he was William Thomson. And he grew up in a very academic household. You know, his father was a professor at the University of Glasgow in mathematics, and his brother was also, you know, interested in mathematics. Their mother died young, and they just went along to the maths lectures. And so he was clearly a precocious child. So he and his brother usually came first and second in the maths competitions. So he was brought up in a very mathematical environment and a very inquiring environment. And he had a very lively mind, and that, you know, he wasn't afraid to sort of just look at, and that it's a feature of his life that he would get interested in things, and then he would sort of move on to the next thing and move on to the next thing, and he went through, you know, he started off thinking about mathematics, and that took him into thermodynamics. And at the time, it wasn't taken for granted that maths was an important part of science. So, you know, when I did my physics degree, the maths lectures were as important as the physics lectures because you couldn't do the physics if you couldn't describe it using mathematics. Well, when William Thomson was growing up, that wasn't the case. So he sort of spent his life as a very good mathematician, to some extent trying to convince other people that the mathematics was important, that if you looked at the maths, you could say important things about the world. And then, of course, later in his life, you know, he went through all these different topics. He was a professor at the University of Glasgow almost his whole life, but he did that in the winter, and in the summer he had time to go do all these other things. But towards the end of his life, and he came up with these ideas. He was interested in lots of things. I'm sure we'll talk about them. But then towards the end of his life, he kind of found that the mathematics had run away from him. And he started to disagree with people like Maxwell, who said, oh, well, you don't need a physical idea. Let's just follow the maths and see where the maths takes us. And he really resisted that because he was like, where's your physical idea behind this? And so even though mathematics was what gave him his career, by the end, he didn't trust mathematics to take you off into the unknown. He wanted to be able to see what it meant. And so towards the end of his life, as is the case with many famous scientists, he'd held on to the ideas of his youth, and he had to the baton was taken from him, really, to move on to the next generation. But yes, he had a very lively mind, and he was interested in making practical things in the world work.
And it's worth saying with James Clerk Maxwell, who you mentioned, even though William Thomson was sort of resistant to the ideas of James Clerk Maxwell, who people might know as the person who came up with the laws of electromagnetism, or brought together all the understanding from people like Faraday and other people. Even though he was following the maths, and William Thomson sort of didn't like that so much, it was William Thomson's ideas that got Clerk Maxwell onto that in the first place. And any biography of Maxwell you read, or any of his papers you read, he acknowledges the depth. He says it was William Thomson who put him onto those things, allowed him to create the laws of electromagnetism, which are probably some of the greatest achievements of that time, the late 19th century.
So perhaps the biggest thing that, for me anyway, is the Kelvin scale. And maybe, Helen, I can turn to you, and maybe you can tell us a little bit about what this is about and why this is important for us as in our lives.
Well, it's almost hard to remember back to the sort of 1820s, 1830s, 1840s, when people understood that heat was a thing, but what kind of thing was it? There was no formal definition of energy. You could see that there was something you could measure. You could make a thermometer, but what exactly did it mean, and what was it that, when you have a hot thing and a cold thing and heat flows from hot to cold, what is moving, what is actually happening? All of this wasn't clear. And so in the 1830s and 1840s, there were a group of people who were working out what would eventually be called thermodynamics. And so, and it all, a lot of this was based on the science of steam engines and thinking about steam engines and how if we have heat, we can somehow get useful energy out of it. But how much energy are we going to get out of it? And how do we make it more efficient? And how do we make these steam engines work? And so, there were early concepts like the heat engine, which is a theoretical concept in physics, which has been extraordinarily useful. And it's basically what runs modern refrigerators today. It's not left in the past. And it's this idea that you can go around a cycle and you can keep going around it. You add a bit of heat here, you get a bit of work out there, you go around and around this cycle. It's a theoretical construct that lets you calculate efficiencies and things like that. And so they started working towards this, and people started grappling with the idea of what energy was, and this idea that mechanical energy, so if you move something, you could convert that into heat and back the other way. So J.P. Joule was, the sort of person who was doing these experiments where he was mixing things with mechanical paddles, and he could see the temperature rise. And that was a really difficult experiment to do at the time. But he could measure a temperature rise. So there's starting to be these ideas that we would now call conservation of energy. And they're sort of creeping forward. And you can see in the literature that people are sort of having ideas and then they go a bit off in the wrong direction. And all of this kind of, it gradually moves forward. And afterwards, in a slightly inelegant way, they all have big arguments about who got there first and who was responsible. And actually, it held some of the science back because they were busy arguing, was it the British or the French or who had the right idea? Nothing changes really, does it? But then they get to this point where they can see that. And this is before they understand what temperature is. So now we have this idea of temperature of atoms moving around. They were not certain that atoms existed. It had been proposed, but there was no mechanical model of atoms. What is it? But they could still see that using gases, that if you heat up a gas, it expands, and if you cool it down, it shrinks, and you can draw the line of the sort of temperature and the volume. And it seems that there's this point where it goes down to this temperature and you can't go any lower. And this concept of absolute zero was kind of knocking around, and a few people had sort of hinted at it, and there is a debate over who exactly wrote it down. But Kelvin wrote a paper in, I think, 1852-ish, where he sort of set this out as an idea. And then, 100 years later, this scale was named after him. And the idea of the Kelvin scale is, of course, that whatever the lowest temperature you can get to that's zero, and you count upwards from there. And then the Celsius scale starts some way up, and that's where our zero is, and then you can keep going. But in the terms of how the structures of thermodynamics worked, that's one of the things that makes it all make sense, that you have this idea of temperature where you can't go any lower. Because initially it was thought you just go down and down and down and down. But it's one of the building blocks of thermodynamics that there is this 0 point, and that Kelvin's name is attached to that scale.
Yeah, it's amazing, isn't it? If you think back that period of time, how amazing we were intellectually as a country to be able to deliver on these sort of ideas and research and innovation, etc. And I know you studied astrophysics. You told me earlier on. What can you? Was there anything in what you studied at university that you can perhaps draw parallels on in terms of the level of sort of ideas, concepts that Kelvin produced? Is there any sort of similarity between other sort of astrophysics sort of interventions, etc.?
Well, I mean, so I studied physics as well at university, and specifically astrophysics and sort of the structures of galaxies and how they emit light in different frequencies and so on. And I did a course in thermodynamics. It's absolutely fascinating. But when you study those subjects at university, you're given basically a set of equations to memorize and derive, and you're given some history of how they came along. But really, you've got to get through a lot of information to then get to your exams, to then go into the quantum mechanics lectures, and you've got a lot to learn. So you don't have any time to think about the sort of stories that Helen's been talking about. And later on, I would read stories about thermodynamics and how it came, and steam engines, and James Watt, and all those people who were involved, Joule, Clausius, all these people whose names were just names of constants or equations until I'd read stories about them, including actually Kelvin. Kelvin was just the name of a scale until you read actually who he was and how he fitted into things. And Watt was just a measure of power, right? rather than an actual engineer who argued with all sorts of other people about various things in those times. And so you don't hear those stories, but I'll tell you, the one thing that struck me was when we did our thermodynamics course, we learnt about all of this, steam engines, heat engines, etc. We learned about the laws of thermodynamics. And then you hop over into the cosmology course, you realise that basically all of cosmology is just thermodynamics on a massive scale. And there's no reason at all why someone studying the efficiency of a steam engine should understand how the galaxy evolves or how the universe evolves, which is ultimately based on the same three equations. So it shows you how powerful a bit of engineering can be in terms of actually doing basic physics. And there's this sort of arrogant physics way of looking at the world, which is we come up with the equations that describe everything, and then engineers work it in the real world somehow with lots of problems and things. But actually, thermodynamics was the other way around. It was engineers who really invented it, and then it was the physicists who were like, this could be interesting, this could be important. And then, of course, it defines the evolutions of galaxies. It defines possibly the end of the universe. If one of the theories about the end of the universe is that things will just keep expanding, and if that's the case, the cosmological constant is near to zero. It will just keep expanding forever, and you'll get to something called the heat death, which is almost absolute zero for the entire universe. It's not quite, but it's almost absolute zero because if you understand what temperature is, which Helen can talk about, which is something we didn't understand 100 years ago, but now we've got a basic understanding of temperature, which is not really how hot or cold something is. It's about how much something is moving at the atomic level. They didn't know that at the time, but if you think about the fact that everything in the universe will eventually lose energy, the entropy sort of minimizes, you get to a point where technically everything should be still, so the temperature will be almost zero, and so that's the heat death of the universe, and so that's where we're going. So that the laws of thermodynamics tell you that they tell you that that's where the universe is going in a very simple way, and so it applies there, and then it also, of course, applies to biological systems. It applies to all the engineering systems we use. So the fact is that these simple rules that you can write down in less than 3 lines turn out to be profoundly important for everything. It's not just refrigeration and heating and cooling and things, but it's about the way energy moves in the universe. And fundamentally, that's all it is. And we're just a temporary aberration in the energy being in a certain state. But ultimately, the energy will be completely following the rules of thermodynamics forever.
But then, Kelvin himself did generate a bit of controversy on all of this, so that the first papers he wrote were on how heat is distributed and all that, how heat moves around. Even though they didn't know what it was, he could still write down.
They called it caloric.
Yeah,
that was the substance that moves around.
But he was so insistent on the rules of. He got very cross with people who didn't believe that the physics said this, and so he early on he thought about the implications of heat leaching away, and he said, well, maybe if you could measure the heat loss of the Earth, you could put an age limit on this, on how old planet Earth is. But at the time there wasn't any data, and 20 years or so later, somebody measured some, heat loss, and he did the calculations, and he came to the conclusion that if the Earth was just cooling down and it was losing heat, and you look at the way it is now, his initial numbers varied a bit, but I think his initial calculations were somewhere around 20 to 40 million years, and then it came down as the numbers came down. And so he was insistent that because the physics said so, because of this physics of heat loss, the Earth could not be older than 100,000 years, I think, by the end of his life. And the problem is, he didn't know about radioactivity. There were these. So he was very insistent on this physical model, but he didn't. There was a part of the physics that was missing. But he was like a dog on a stick. He wouldn't let go of it.
To the point where he argued with Charles Darwin about the evolution
about
of
the age
species,
of the Earth.
Because obviously that was the same time. An amazing flowering of intellectual achievement in the 19th century. Of course, you've got Charles Darwin going on his adventures and coming back and thinking, I think evolution of species happens over a long time scale, which was causing issues for his Christianity, and so the Earth must be very, very, very old. And when Kelvin came up with his ideas of how old the Earth must be, there just isn't enough time, even 20 million years, to do the things that Charles Darwin was suggesting. So he was unfortunately quite against the idea that it could explain the diversity of life on Earth. But of course, as Helen says, he didn't have some key crucial bits of evidence. And I'm sure if he's arguing it today, he might have a different opinion
But he was also arguing with the geologists, because the geologists sort of went, we don't need any of your numbers, thank you very much, we're just getting on with our geology. So there was this, they were like, oh, well, it's infinite. There was this idea that the way Earth exists now is the way it's always existed. We don't need to have an age, it's just always been like this. And so he was also very frustrated with their dismissal of the physics. That was just one of the cases in his life where he was like, why, there's these numbers, why are you not listening to me? We can measure things and we can calculate things, why are you not listening? And the geologists were like, just get on with your numbers over there, we don't care. So these tensions about how science operates and how important mathematics is, that basically followed him through his entire life.
So would you say he was an engineer, a scientist, a physicist, or actually all of those, or does it matter?
I don't think it matters.
He was a mathematician.
Yeah. But also he wrote the book on physics. I mean, the textbooks didn't really exist, and he, in the 1860s, I think, got together with this guy, George Tate. And they said there's all these ideas about, how energy flows and how heat works and maybe a little bit of electromagnetism and light. We want to teach our students, and we need to just put it all in one place so our students can learn this more quickly. And so the work was it was Thomson's idea, and then George Tate sort of did the legwork on it and kept, come on, Thomson, can we do this now? Can you hurry up? And he writes in these letters where he says, can you look, I sent you this thing, can you please just look at it and send it back? I mean, the process would be familiar to editors of journals today, I think. But they come up with this textbook, and this textbook contains what becomes classical physics. And of course it doesn't, it's at the 1860s, they don't know everything yet. But the concept of there being this subject where all these things come together, Thomson saw that this is the collection of things that make sense. And so he literally wrote the textbook that became physics. Yeah. But I don't think it matters.
He was a professor of natural philosophy at Glasgow University. And natural philosophy is what we now call physics. And I don't think physics as a subject existed until Thomson came along and codified it in that way. Obviously, people were doing it in all sorts of different ways, but that's where it comes from, as a mathematical concept, as something that exists outside the sort of achievements of humankind. If you think of engineering as the application of all ideas of physics and chemistry and other things into technical things that humans use, then physics is the concept behind it, right? So to your question, was he a physicist or an engineer? I think he was both, and a mathematician and the inventor of physics as a subject, right? Even Isaac Newton would not have recognised the word physics. He was a natural philosopher. And I think it was the 19th century that created the word and the subject.
Yeah. But he also, just outside of the work, he was also, I believe, a very good musician. And also he rode for his university as well. And I just wondered if there's any more that you can bring about his private life, and actually how it all sort of, because it seems like he's an amazing individual.
I think he did a lot of lecturing as well, didn't he? To not only other scientists but members of the public. He was probably the most famous scientist of his time, even though he wasn't that famous. He was still famous enough to be ennobled. He's the first scientist to be ennobled. He's also eventually a member of the Privy Council, Order of Merit, all these things which we hoped our best scientists today are part of. But scientists or those kinds of people doing natural philosophy weren't seen in those ways in that time. I think that he really was the first public scientist, if you like, as well as being the inventor of things like physics and thermodynamics.
Well, he wasn't a snob, was he? I mean, when he was at university, as you say, he bought this boat. His dad, who was the professor in Glasgow, was terribly worried that he was not going to apply. He was going to have too much fun, and he wasn't going to do enough maths. He wasn't going to work hard enough. So when he wrote to his dad that he was going to go rowing, his dad was terrified. And I think the sort of religious background they had meant that they were a bit worried about Cambridge being this sort of not quite a den of sin, but a thing full of distractions that might take a young man away from his studies. And so he bought this boat without telling his dad, and then wrote to him and said, "Oh, can I have the money, please? I bought this boat. It's terribly nice." But and he wasn't afraid to have fun, but he also wasn't a snob about it. Like, as you look through his life, he did all these interesting things, and part of the reason he did it is that he didn't think he had to be a serious academic doing serious things. He was interested in making things happen in the real world. And that's how he got into some of these engineering challenges. And of course, one of them made him a lot of money, the transatlantic telegraph cables, which we'll probably get to, made him a lot of money. And after that, he had a lot more freedom then he could do what he wanted, and he didn't have to pay any attention to, there was no peer pressure telling him, oh, well, you have to do this. Because when you've just made all this money, you've just made transatlantic telegraph cables look like a near reality, but you can do what you want. And he really used that. He didn't feel that he had to be this kind of scientist or this kind of mathematician. He had these talents, and he was just interested in making things better in the world.
Yeah, which is an amazing position to be in. But maybe you can tell us a little bit more about that transatlantic cable and maybe some of the other ideas that he introduced, navigation and some of these other things that he did as part of his life. It wasn't just purely thermodynamics, was it?
No, but so he also looked at, this is the time of Faraday and electromagnetism was coming along. And Faraday and Kelvin were quite an interesting contrast because Faraday was very intuitive. He couldn't do maths. He was very, very good at experiments. He was very, very good at observing things. And he's the one that drew the lines of force, and sort of put a picture on it. But he didn't have the maths to describe it. And Kelvin was very, very mathematical. And he sort of didn't, I think he respected Faraday, but he didn't see the world in the same way. He wanted to describe it using, equations. But anyway, the thing about the telegraph was that if an electric signal is sent, it's fine for it to come down the cable, but you've got to detect it at the other end. And so one of the invention that made William Thomson, Lord Kelvin, his money was this thing called the mirror galvanometer. So it's basically Faraday had found that if a current ran through a wire, it could make something twitch, make something magnetic twitch. But how sensitive could you make it? And the contribution that William Thomson made was to make an extremely sensitive thing, so that even if the signal was very weak, you could still pick it up. And he did it with a little suspended mirror with a light shining on it, so that if the mirror just twitched, the light was deflected to a different place. It's a very simple idea as far as we're concerned today. But what it meant was that if you had a very, very long wire with a very weak signal and you had this thing, then you could read your telegraph signal. So it's the difference between the wire being useless and the wire being a communication device. But what was interesting about it is that, so people had this idea of transatlantic cables, which were relatively primitive. You've got this sort of gutta percha rubber stuff on the outside of the cable. And they didn't know how to lay transatlantic cables. No one had done it. No one was very good at it. And so he went, so there were they didn't get it right first time. It's a long way across the Atlantic. And the initial idea was that you started with two boats in the middle, and you gave each of them one end, and they sort of went in opposite directions. But William Thomson was on these expeditions. So I think he went on 5 cable laying expeditions where they would lay it, and of course they're checking all the way along, because they don't want it to break. So you start laying the cable, and you're checking: can I still hear it? Can I still detect it? Can I still detect? So he was sort of on the ship, check, and if the cable broke, then they had to either fish it up or reconnect it or give up in some cases. And so there were these expeditions over many years, and people are gaining and losing money. We're all going to invest in a new idea. We'll send out another ship. The Great Eastern, Brunel's great ship, was one of the ships that was sent out to do this job. And William Thomson is on these ships making the measurements, and he stays there. He was unpaid for all of that. He just did it because it was a good idea. But then when he got, and sometimes they worked and sometimes they didn't. Sometimes they didn't last very long, but the direction of travel was clear. But what made him the money was that once it was clear it was going to work, then he had the patent on this mirror galvanometer. And then everybody wanted to use it. And suddenly, these licenses started to come in, and suddenly he became a wealthy man. He'd been well paid before, but this was the step up. This was the thing that allowed him to live a different lifestyle and travel a lot and had a lot more freedom. And so it is quite amazing. And it took them, I think after he did 5 until they'd mostly got it right. And then he sort of got, lost interest a bit, went off and did other things. He made his money from that, and then he carried on to other ideas. But he was right. He wasn't just writing the theories. He was making the devices that made it possible, and he was on the ship actually making it work. And really, when you look at the inventions that he developed later on in life, a lot of them, people sort of say, oh, well, he didn't come up with the idea. He used other people's science, but he made it work. And that was the engineering side of him, that if he could take these different ideas, here's some designs, people have got the right idea, but it doesn't quite work. And he would bring them together and go, here's something that does work. And a lot of the invention he took out lots of patents in his life, but that was what he did. He wanted to make it usable for the common man who didn't have his mathematical skills, for example. And those are all sorts of things, sort of compasses and bits and pieces in all these different areas. So he was very prolific, but he was a butterfly. He'd do this for a bit, have an idea, leave it to somebody else to carry it, to make it, to scale it up, and then move on to the next thing.
And it's because of the cable that he got his knighthood in the cable was laid in 1866, but then he got knighthood. And interestingly, what that meant was that Britain became the world's preeminent communications country, basically. They were able to do it. And it's probably one of the reasons why the country succeeded in many respects, that other people couldn't communicate in the way that it could.
If we were to look to today, and if it's possible to sort of think if there's someone in our lives today that would sort of mirror Lord Kelvin, is there anyone you could think of that would be, you could, I know it's always very difficult to compare, but, the same sort of gravitas, the same sort of intellectual ability, the same sort of person that has impact on the world, who would you think?
I think it doesn't work like that today, because there was a period of science where you basically could know all science, which was a bit earlier, but then there was a period where you could know all physics and you could just apply it to whatever you wanted to. You could sort of know everything that was known about heat and light and temperature, and then and apply it. And so I think in that, the people in that period who had that knowledge were easily able to be very influential, because they could tie the pieces together and they could just do lots of different things. I mean, I'll mention the temperature scale, but if you really look through physics textbooks, there's all kinds of things. There's Kelvin, Helmholtz instabilities, and there's there's the list of things named after Kelvin is really, 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 really long. And it's not just physical theories; it's inventions as well. But it's because he was able to dot about between subjects. So I think we don't have people like that anymore. We have many brilliant scientists and engineers, but what we don't. They're still fundamentally experts in one area, and they may have a view on the rest, but they don't have deep knowledge of everything we know. Yeah. And I think that century, the 1800 to 1900, that was the period when you could have a very broad knowledge. I don't know, do you think there's anything?
Yeah, I think that's right. And I think that actually it's quite a big ask to think that an individual person could not only contain the engineering and scientific knowledge about something that's a new technology, and then create the commercial thing around it as well. I mean, perhaps the world was smaller back in the 19th century, but I feel like if you had something equivalent now, you would need a corporation which is hundreds, maybe thousands of people who are technically expert at one specific bit of something. Laying an undersea cable today is you're talking about understanding quantum mechanics and optical fibers and data information rates and stuff, which is incredible. They're all different skills. You can't. I mean, yes, there might be a chief executive of a company who's laying a cable, who you might put in the Kelvin mold, who might understand that these things are important, all these different sciences are important, but there's at least 30 different scientists types, each with their own teams of people working on optimizing something specific. And again, it's all abstracted from us because we just connect to the rest of the world, right? But the physics and the engineering has become so complicated that I think we shouldn't expect a single person to embody it. Perhaps a corporation or a person can embody the arrangement around it. So there are definitely technological superstars these days, for good or ill. But they couldn't do what Kelvin had done. There are people who build rockets, right? But that person doesn't literally turn the spanners or detect the instruments and things. There are thousands of other scientists doing it in the background, and we should be aware of that. We should be aware that this is a complicated orchestra, and it's just a different world.
Yeah, that's amazing to think through what he achieved. I guess he probably wasn't single-handed, and he must have had a team around him. But even still, it's still the breadth and depth there. If we were to sort of look forward to today in refrigeration, how would you think Lord Kelvin would sort of come into this world today, and how would he perceive cooling in general, and maybe some of the challenges that we've got ahead for us?
You probably have to get him across some of the things that he didn't really believe in, like atoms and quantum mechanics and radioactivity.
Turns out they're important.
Turns out there's a bit of catching up to do, I think.
Yeah.
And maybe these technologies, GPS, for example, and the whole question. So he died in 1907, I think. So Einstein's 1905 papers had been published. What he knew of them, I don't know. But that whole revolution in thinking, that he was before that. So I think, and I don't know how he would respond to the quantum mechanical world, but because he was so focused on mechanisms, he argued so hard at the end of his life, especially with Maxwell's papers, that he was like, well, what does it mean? Give me a model, give me a physical model, and I will explain it to you and predict it. But if you don't have a model, it doesn't mean anything. And now we have an entire civilization that is built on quantum mechanics, which doesn't mean anything. You know, like there is no physical analogy. We come up with very poor analogies, but we should understand that is not what's actually going on. That's just to make it easier for our brains. And it is the maths that tells us things. And I think he would have hated the idea of probabilistic. I think he would have hated Heisenberg's uncertainty principle with a passion.
And yet, thermodynamics is incredibly important to that world. It's all basically energy flows, and you use the same basic physics to explain how energy moves. Now, it's probabilistic, sure, but it's still it doesn't break the laws of thermodynamics. In fact, it can't break the laws of thermodynamics, which obviously he created. But I think to your point of like, if we transported William Thomson and Lord Kelvin here right now, he'd first of all be very surprised because he thought all physics was done by the time he was finished. Remember, if we say that he kind of invented the book for physics that people learned, classical physics, which was then tied up by James Clerk Maxwell with his laws of thermodynamics, the equations of thermodynamics. That really is the nice, neat tying up of physics. There was nothing else to discover, remember? And he said it himself, that this is done, we don't need any more. And it was just at the time when Einstein was coming up with special and then general relativity, and then quantum mechanics was happening. So he kind of, there was a neat juncture of his life ending, and then the entire of physics being completely transformed. So he'd be very surprised, I'm sure, because he was convinced there was nothing more to learn.
Yeah, so Helen, you mentioned earlier on about his ability to be able to look back in terms of the calculation of the world temperature. And one of the challenges that we have today is actually looking forward to climate change. And I just wonder whether there is anything that he would be able to bring to this discussion about climate change, and specifically the impact of cooling on climate change in as a mitigation, but also as a cause as well. And what thoughts did you have on how we might be thinking about this if he were here today?
Well, the fundamental laws of heat flow and the way heat moves are pretty much the same ones that he wrote down based on Fourier's work. So I think he would definitely recognise a lot of the equations that are still in, obviously styles of writing things down have changed, but he would recognise the fundamental form of the equations. I don't know how, he wasn't a fan of this uniformitarian, I can't remember the word for it, but there was this geological idea that the world hadn't changed, and he was not in favour of that interpretation. So he was aware that planets could change. It made sense if Earth wasn't didn't look the same today as it had looked some number of hundreds or thousands or millions of years ago, depending on how long you thought the age of the Earth was. So I don't think he'd have been surprised by the change, but he was very practical. I think what he would be doing if he was here now is looking for the practical problems that could be solved in order to make something better. Like, he was very focused on give me the real world problem and I will solve it for you. So I think he'd be very pragmatic about what we can do and how we can change the technologies we run our lives with. And he would be interested. He'd be that sort of Erdish figure who sort of comes in, has an idea, and then clears off and has another idea over there. But yes, he was a very practical man. I mean, his brother was an engineer. He grew up in the time of the great engineers, and he saw his science as a route to do engineering better. So I think he would be very focused on the engineering solutions.
Alex, did you have any views on potentially the challenges ahead for us as a country, and potentially how?
Well, I talked earlier about climate change. I think you've alluded to it too. And there's the issue of the fact that we're going to have to use more cooling of some sort to make people's lives more comfortable. That also applies to all the things Helen mentioned earlier, which is when it comes to cold chains, medicines. These things will have to be stabilised more. So the need for cooling is not going down, it's definitely going up as a result of the Earth just generally warming and humans living in those places where temperature's going up. So I think the big challenge is, how do you do that without increasing without contributing further to the problem that's caused all this in the first place, which is carbon dioxide emissions and burning fossil fuels. And the big question is it comes down to energy, right? Where does your energy come from? And fundamentally, thermodynamics and the kinds of things that Kelvin was interested in when he was coming up with these things, it was all about the movement of energy and the storing of energy. And I think that when I was thinking about this question earlier, I was thinking, well, what challenges might be interesting to someone like that now? It's energy storage. It's energy, moving of energy efficiently. It's not finding sources that are sustainable. We have those. It's how do we make them useful? Solar power, a great source of energy, but very difficult to spread around the world, right? In many ways. Although that's getting better. Things like wind, things like geothermal, all these things. This is about movement of energy and storing of energy. It's the greatest challenge in the next 10, 20 years. And actually, do you know what? It's not the sexiest challenge. Whenever you think about it, you think, oh, what's the next latest in battery technology? It really is so important. And you kind of need a big figure to sort of say, I'm really interested in batteries. I'm going to make batteries the best possible batteries I can. And it's all about thermodynamics ultimately. So I think that's a challenge which could do with some interdisciplinarity and the kind of mind that would understand how to sort of solve problems in the real world, as I said earlier. I think that would be a great challenge for someone like that. And I think that's maybe where he would go. I can't read a man's mind, but it would feel like this, the same way as the transatlantic cables. This is a challenge that has an incredible impact on the world. If you could solve batteries or make batteries so much better than they are today, that would be tremendously useful to set up the world for a much more interesting, better future. Cooling is important. That's one thing. But you could imagine that this is an even bigger challenge that might be interesting.
Yeah, so a big figure and dealing with big impact would be really helpful for us today, because cooling is a little bit hidden in the UK, and it cuts across many applications, and it has a big environmental impact. It's a mature industry as well, and when we're trying to communicate these careers to young people, often it gets slightly hidden behind AI and all these other perhaps new areas, and perhaps Lord Kelvin as a big figure would really help could publicise this to young people. But did you have any views about how, as an industry, we might be able to have the Lord Kelvin impact across young people, etc., to engage them?
But you're the expert in this, Graham. So refrigeration is not a topic that's gone away. You need better methods to do it, right? And of course, an understanding of thermodynamics is part of it, but also the engineering challenge is to make it use less energy, make it much more efficient. If we've had this technology for not even 200 years, really, how do you make it more efficient? You definitely need people who understand artificial intelligence to make that work. So it's not that if you're interested in artificial intelligence, you can't make refrigeration better. AI can be used in all sorts of ways, and there's lots of hype around it and things, but genuinely the hard, wicked problems that exist in things like making batteries better, or making refrigeration more efficient, or reducing the amount of chemicals that are perhaps not so great for the environment in use in refrigeration. These are all challenges that can be that are amenable to people with different skills. That you need an understanding of how energy moves around and a better modelling of these things. Take data centres, for example, which are probably going to be one of the most cooled sectors of society. Never mind humans living in cool places. Computers need to live in these places. If you want to solve refrigeration for those places and make those cooler with less energy, I'm sure that the big tech companies are going to pay you a lot of money to do that. And that they're working on this stuff, right? So refrigeration is not just about making human lives more comfortable or making cold chains work. It's much more than that. And I think that if you as a professor in the world of this want to make more people interested, I think that it's worth saying to people that you need technologies and ideas from all sorts of different angles to make this better for almost a whole new bunch of uses.
But I think also the reason I think refrigeration is going to become much more apparent is because of heat pumps. Because suddenly with a heat pump, even though they've been around for a while, but now they're sort of rising up the agenda. You have this concept of moving energy around and moving heat around. And in the past, it was always about you turn a switch and you turn something else into heat, and heat just appears. But once you have this concept of moving heat around, that actually you start thinking about how heat in the world is distributed. Is it all in data centres when actually we might want it in our swimming pools or whatever it is? Then you start to see it as a resource that can be moved around. And I think that framing of the problem, when you start to see heat, because heat, I mean, there's lots of energy in lots of different forms, but you have a lot of energy in heat. And some of it's useful and some of it isn't, which is another, as we look for more renewable technologies, we have to look for renewable energy in the places where we have useful energy, not just energy that's so diluted it's not particularly useful. So I think there's a framing of the world in which the distribution of heat becomes the problem, and that is the sort of big challenge that you can state it. Once you see the world like that, you can state it, and then you start to link these technologies together, your data centers and your home heating and your home water supplies, and the places where you have too much heat and you want less, and the people where you have not enough heat and you want more. How do we tie all this together? It's like a smart, it's like the sort of smart fridges and things. What's the word I'm looking for?
Integration?
No, it's the Internet of Things, right? It's basically an Internet of heat. It becomes how do we move the heat around? And that's the bit where then it's a problem that becomes interesting because it's a really foundational problem, and yet we still haven't solved it.
Yeah, those are really nice ideas from you, both of you. Actually, it's always good looking from the outside in and saying, how we can make things attractive to others. The Internet of Heat is a really nice phrase, which I think we'll probably might steal for something else at some point. So it's coming to sort of towards the end of this discussion, but I'd just like to ask both of you what you would see as being what's the best story that you have from what you've done, from what you've analysed about Lord Kelvin. What's the most exciting thing that you wanted to sort of pick on? Maybe start with you, Helen, first, if that's all right.
I think the best thing about him isn't a single thing. I mean, there are the nice stories are the stories where he's human in some way, but really it's the variety. That's what gets me about him. It's just the variety of things that he did, and he just wasn't afraid to be interested in lots of things. And I think that is a great thing. So. I mean, my favourite stories of him are probably him writing home to his dad, begging for more money for a boat. He was a great believer in life in doing it first and asking for forgiveness afterwards. That wasn't the first time. He started off doing that with the boat with his dad, but he definitely did it later in life when building laboratories and things like that. He was just going to do it, and then he'd say, "Oh, by the way, I've done this. Is it okay?" But it got things done. So he wasn't afraid to just, think about the world in its broadest sense.
Brilliant.
I think my answer is a slightly different version of what Helen just said, which is that, and I've made a note about this earlier, which is that when reading about Lord Kelvin, what struck me was the interdisciplinarity of what he was doing. He was interested in a lot of things, as Helen says, and I think that is where you get the best solutions for things. When you've become an expert in something, but you can't. When you become an expert in something and you can't see what it's like not to be an expert in something, I think that's a problem for modern society generally. I think it's a problem in many ways. It's a problem in explaining yourself to the world, getting people to be interested in what you're doing. But when you can see your own work from the outside and then work out how somewhere in the middle there's a solution to something or a problem that someone else is thinking about, that is quite valuable. And I think that it might have been easier to do this when physics was more limited and engineering was more limited. So I say this with caution. But being able to sort of step outside and have fun with things and not take everything you do to the nth degree and be so serious about it that you can't see it from the outside and just sometimes sort of have, be a bit silly with it and things. I think that, or give lectures to people who don't understand, and give time up to that sort of thing. I think that if you can't do that, then you get siloed, and many scientists I know, and you probably know as well, suffer from this. And I think that perhaps he's an example of someone who was able to step outside his own world, understand things a bit more, maybe learn some more things, but also kind of work in that world of interdisciplinarity, which made him more practical and useful and interesting.
Brilliant. Thank you both. So I think we're just going to wrap up now, and I'd just like to wrap up by saying that this is celebrating Lord Kelvin's birthday, his 200th birthday. At the centenary of his birthday, an eminent physicist, another British physicist, Sir Richard Glazebrook, proposed a toast to the debt that we owe Lord Kelvin. And I'm going to thank our speakers, and I'm going to prepare a toast for you all, and those of you that are online, I hope you will do the same as well. But so if we pick up our glasses and we can propose a toast to the debt that we owe Lord Kelvin. Cheers.